And yes, I was made aware and I solved it, but I don't think I updated my answer key yet. One of the pages was blank, right? Didn't have a key there, so I will bring that up as well. But on page 16, right here you have first and foremost you should realize, okay, that value right there, b, or whatever has the exponent attached to it, that is the b value, and it's less than 1. So this will be a decreasing function. But I think what I found interesting, that's why I added this one, what you see that this is a y here. And so some students might be like, oh, so that's my y variable, right? No. You always know that whatever is to the right side of the equation, that is your x value. That's what's going to be along the x-axis, okay? So maybe that threw you off, but I just went and read what is y in this scenario. Okay, it says here y is the thousands of years of age of the sample. So maybe instead of having a y there, you might just want to say, hey, that's thousands of years. That represents my time here. Why there's a y, I didn't make this one up. I just got this from somewhere. Okay, so I'm just letting you know that if that ever happens to you, don't deviate from our plan. Okay, whatever is to the right of the equal sign is x. It's along the x axis. And c is the parts per million. I don't know if you've ever seen ppm before. If you're in chemistry, you probably know what ppm is, but it's parts per million. That's how you measure concentration of something. So that was a question there. And remember, exponential functions never cross the x-axis, so your graph should never touch the x-axis. They're very picky with that. So even if it's sort of like you didn't mean to, but it does touch, like we're going to take marks off. And so there you have a decreasing function. And maybe I should just talk about your window. Zoom fit is a really good friend for this particular function. Zoom fit for exponential and logarithmic. If you can't make it work, so if you want to follow me here, because this is like a homework check, I don't do this very often, and how do you input this? It's very important that you know how to enter this correctly. Because your exponent is a fraction, I would say make sure you press the hat to have the exponent there, and then I would type that in as a fraction. Okay, so x divided by 5.73. So that's how you enter that exponent. Don't do that separately because I cannot guarantee you success if you don't have the brackets. Okay, and then I hit graph. I happen to see mine because I did something else before this, right? So I'm gonna go zoom 6 to go standard window, and I don't see anything. I know that my y-intercept is 0, 450, right? Like I'm way up here. I'm coming down from 450. So that kind of guides me, but let's try zoom fit. So zoom and then 0. So there you see that it lets you see the curve pretty good, except for we don't really care in this particular case. We don't care about that part of the graph. So you can now go to your window and change that accordingly. So maybe x min, I'm just going to go -1. And definitely for y min, you should also have a bit of a negative there. And I kind of base it on the numbers that are there after zoom fit. And there you have your curve. Okay, and we know that it never touches here, but you may have to increase this based on what I'm asking you for. Okay, so that's a good graph. Make a graph for the equation for a time of 30,000 years. Okay, so they're giving you kind of an indication how far you should go along the x-axis. Okay. And this is probably a tricky one, right? Make a graph. So this was similar on our test. Okay, because x represents thousands of years. right? We go 10, and we're understanding that that's 10,000. So you would multiply this by 1,000 if you want the actual number, right? 20,000, 30,000. So I just went to 30 because it's understood that it represents thousands of years. Okay? So along in your window here, for x max, maybe go to 40. Okay? And then you see a bit more. I think even my y max is a little overkill. I could probably bring that down to half of what it is right now, but I think that is good enough. Okay? And how do you graph this on paper? Okay? Well, you definitely want the 450 to fit in there. And it told you to make a graph all the way to 30,000, right? So that lets you determine, that gives you enough to figure out the shape. So you know this point 450, 30,000 can be found, right? I actually did the work right here. When x is equal to 30, y is 11.94. So that guided me with this point. And if you're wondering, if you did the homework and you're like, why are there so many points? I just try to find, I did 2 extra points. If you did 1 extra point, that is fine, but then at least you know what the general shape will be. Okay, so I use second trace value, and I enter something along, like in between the y-intercept and the 30 in this case, right? I want to find something to help me out when it comes to graph. Okay, that's 16. For 17, what is weird about that one is that E, and that's why I talked about it. If it ever shows up, you know that that's just, right, that is really 2.7 something. And so the way you would enter that one is 20, and then I would just go second division calls E up, like that. And then you can raise that to the exponent of that, 0.0478x. Okay. You type that in, and this is going to be an increasing function because b, like, right, whatever is under the exponent, that is bigger than 1. So if you graph that one, see, you expect it to go up like this. And then I kind of will let the question guide me a little bit. I know that T, that's time in hours, N is the number of bacteria. It asks for a graph for the first 48 hours. So I'm going to change my X max to, let's say, 50 or 60. Okay. And this is a little bit too high. The Y max does not have to be that high. We can probably bring it down to like 600, let's say, and zoom in a bit more. But that's a pretty good start, and then you adjust accordingly. You adjust based on what I ask you for. Okay, so you have 0, 20, like that y-intercept. That's my starting point, and I did give you 48 is a little bit of a hint there. Okay, so 48, when x is equal to 48, I do the math right here on the side. Y is 298. Remember, you have a calculator. It can find anything you want to help you out. So there it is. And then maybe one more along the way. I found 2 more to help me out, and that gives me a pretty good curve there. How many bacteria after 1 day? 1 day obviously is 24 hours. So, right, you let x be 24 to find the number of bacteria. If it's bacteria, you can't have a decimal, right? You have to have time. Folks, time can be stated as a decimal, even if it's days. Even if it's days, because you can have part of a day, right? It's as a decimal. So time, temperature, distance, money, anything you can measure, decimals are fine. But I think there was this question, what was it yesterday? You gotta watch for the wording. In what year was the screen time the highest? In what year? Oh, like 2014, 2015, whatever that year was, right? But if it asks you how long did it take, then you can have a decimal there. But if it's asking what particular year it happened on, you need to round to the nearest whole number, right? So you got to watch out for the wording there. Was there another? Yeah, I'm going to ask you to go to 18, and I'm going to explain that one more time. You didn't have to graph. I just decided to add the graph there. What is particular about page 18 is this. Doubling time, right? The population doubles every 14 days. That is doubling time. When you have doubling time, you're going to think two things. This must be exponential. Okay? This must be exponential or logarithmic. We'll see later. And I have to make a table. And here's my table. At time 0, I have 400 insects, right? That's how many I start with. And then the population doubles every time. Every time 14 days go by, your previous population doubles. It's important to only double your population. This could be money. This could be various things. So it doesn't always have to be insects or population or bacteria. That's a very common one. And then for time, you start with 0, and every 14 days, the population doubles. So here you add, right, 14 every time. And when you have your table, you can perform the regression and come up with the equation here, the function. Maybe I'll ask you here in preparation for the AC. If you have this one, what is this, an increase or a decrease in population? Increase, right? Because it's bigger than 1. That would be your explanation. By how much is it increasing every year, percentage-wise? 5, right? 5.08%, right? You would essentially go 1.0508 minus 1, because it's always with respect to 1. Okay? And you end up with 0.0508. And if you multiply that by 100, it's telling you that this population is increasing at 5.08% per what? What are we talking about here in terms of time? In this case, it's days, per day. Okay, so the whatever follows the per is determined by what x is measured in, time in this case, right? So there you have it. $19. I don't know if you got that far. But 19 has to do with half-life. And we talked about half-life as well. I'm going to end after this talk right here. Okay. But half-life has often to do with something decaying, right? Decreasing. So the half-life of cesium is 137. Cesium-137 is 30 years. So that's how long it takes for it to go down to half of what it used to be. So at time 0, you're at 100%. Pay attention to this part. I tell you that the initial release is 100%, but they wouldn't have to tell you that if it's percentage that they're talking about. Okay, but anyways, at time 0, there's 100%. After 30 years, you're down to half. Another 30 years go by, half of what you had before, which is a quarter. Another 30 years, this is you don't need that many. You only need 3 points and you're good to go. But sometimes the question will ask you to come up with, I don't know, in this case, this did ask you for 120 years. So that ended up, you stop right here after 1, 2, 3, 4 doubling times, right? and then L1, L2, exponential regression. Here you come up with your formula, with your equation, which if you think about it, this is a reduction, right? Like we understand that this is going down. By how much? Right here, I do the math. 1 minus whatever is in the bracket gives you this, and we multiply that by 100 to give us a 228% per, in this case, year, because time is measured in years. The domain and range is something you need to also be comfortable with. So watch the domain and range here. Because this question gives you a limit, right? You go from time 0 to 298.97. Okay. And 0.1 to 100. But if there had been no limit, you would have gone from time 0 to infinity. It just keeps on growing, or decaying, sorry, I should say. And range, watch this, 0 is never included. Watch this here, if you can see it. If this comes down like that, it will never it will never get to 0 when it comes to y, but really close. So we just don't include it. Okay. But we started at 100% in terms of our y, right? So from 100 to 0, but not including 0. That would have been the range there. Okay. Anyways, we'll see how this goes and adjust from there.